Hello everyone, here I have a simple image classifier which can differentiate between three classes: a square, a triangle, and an X shape. In this video, I will attempt to understand exactly how it works by visualizing its layers. To train it, I drew a dataset of 150 32 by 32 pixel black and white images. 50 of them are squares, 50 triangles, and 50 X's. I split it into 80% training and 20% testing in order to later validate the network. So that means that there are 120 training images, which is 40 per class, and 30 testing images, or 10 per class. For the network, I chose to use linear layers, since this should be enough to get a nice accuracy on the task. The network architecture is the following. The input is 1024 wide, which is 32 times 32, that's the resolution of the images. Then we converge down to 16. I chose this because when visualizing the layers I will be able to reshape them into a square, and the square root of 16 is 4. And the final output layer takes it down to 3 because there are 3 classes. For the activation functions, I chose rel for the input and hidden layer and sigmoid for the last layer. The parts that I will be visualizing are when the input passes between the layers. So that means before the first layer, which lets me see the image, after the first layer, before the second layer, and finally after the last layer, which shows the result. Also, since what actually goes between the layers is one-dimensional and looking at the line of pixels isn't that pleasant, I will be reshaping each input into a square before visualizing. To train the network, I chose the cross-entropy loss function, Adam optimizer, and the initial learning rate was set to 0.001. But every epoch I exponentially decreased it with some constant, so it made this shape. After training for 100 epochs, the final accuracy was exactly 80%, which means that the network made 6 errors out of the 30 tests. That's how the error count decreased while training. And let's just take a moment to appreciate this beautiful loss graph. Now that the network is trained, we can get to the fun part, visualizing the layers. I ran all the testing and training images through the network, visualized them, and put them into these folders. Let's first examine the images that the network classified correctly from the testing dataset. On the first layer, when visualizing triangles, this group of neurons seem to be lighting up the most, and these two seem to be turned off mostly. However, there are some examples that stray from this pattern. For example, this one triangle looks completely different from this one, however they both still were classified correctly. Interestingly, the squares look very similar to the triangles. On most, there's a very defined pattern showing up around these pixels. But on one particular example, there's no sign of that pattern showing. Also interestingly, this connection seems to be lighting up on both the squares, the triangles, and later the X's. The latter looks completely different. The X's create a pattern that mostly look like a triangle shape on the top left and a single pixel on the bottom right. By the way, the one recurring pixel is also lighting up here. My theory about why the triangle and the square patterns look so similar, yet the pattern on the X looks so different, is that it might just be a sign of overfitting, improper loss or optimizer, or something else. This theory also explains the mysterious single pixel that lights up no matter what. Moving on to the second layer, we see that the squares have a pretty consistent pattern that looks like a sort of question mark. It only changes its brightness, not its shape, across all of the examples. Same thing can be said for the triangles. It also has a consistent inverse C-shaped pattern, however here we get a bit more irregularities than the squares. Like in this example, where the pattern looks normal, and in here, where the pattern looks more squished. The X's also have their own pattern. It looks like this. I found it kinda curious that in some cases the X seem to be a little bit confused by the network as a triangle, like in here, where it looks like there is a dim outline of the triangle pattern. I didn't visualize the tensor before the first layer and after the last layer, since the first will just show the image being classified and the last consists of 3 numbers, it's not worth visualizing. You probably noticed that the activations from the first layer between the square and the triangle look extremely similar, and I have no idea how the second layer actually differentiates between them. This might also be linked to why the only mistakes the network made are between the triangle and the square. Not a single mistake was made on the X, whose first layer activation looks quite different. For the second layer, we can see that the patterns look mostly different, which makes sense because after this layer, we go straight to the output. Here I took the average of all the images from the testing set. Like I said, the first layer activation of the triangle and the square look even more similar on the average, but the second layer learned to differentiate between them. Then I tried combining the averages to see if maybe I could find areas which were responsible for detecting each shape, and got this. Although the image looks quite pretty before the first layer, after the first and second, they really get hard to understand. However, there is still some useful information to be learned. First of all, after the first layer, we said that the red area and the brown pixel matches up with the expected activation that we learned from visualizing the axes. However, things get quite weird with the square and triangle. The green pixels correspond with the triangle. It seems to be mainly using the diagonal in the middle, and some more pixels around it. The square seems to only get 3 or maybe 4 connections for it, which is way less attention than the others get. It is also interesting that the pixel on the bottom right is shared between the triangle and the X, since green and red make brown together. On the second layer, things get clearer. First I noticed that there are 4 dark pixels, which seem to be pretty useless, since they don't process any information on any of the classes. We can see that these connections are mostly lighting up when a triangle is shown, these ones when the X, and these ones when a square is shown. Here I've decided to run some tests on images that the network got wrong. These consist of a single square and 5 triangles. I wasn't able to find any common patterns in the error layers 1 and 2 that were specific to the errors, but maybe there does exist some kind of lie detector pattern or a neuron, and I just need a bigger data set to find it. I also thought that it will be interesting to run some visualizations on the training and not testing data, and here's what I found. So I ran 9 examples, 3 from each class, and all of them came out as correct guesses. Besides the pattern being sharper in the training images, I didn't find any noticeable difference in the first layer. Same thing happened on the second layer. The network seemed to act the same as the testing images, besides the pattern looking a little sharper, but overall nothing changed. After running all of those tests, I arrived at these conclusions. Firstly, counting the average of a layer, overall the test data, reveals inactive neurons that don't change their state no matter the class, and are pretty much useless since as far as I know they don't impact the result, and just waste computations. This might be helpful if you count all the pixels that activate below a certain threshold, and then you know the exact number of neurons that need to be pruned. Secondly, it may be possible to shave off layers, because like in the second layer of my example, it was already quite obvious which shape it was trying to classify. The speed improvement in this network may be tiny, but on bigger classifiers, if you find a pattern in the early layers that can predict the results with an acceptable accuracy, you can improve the speed quite a lot. And the third and last one is that it's a complete mystery why the network is able to differentiate between the square and the triangle. Even though whatever comes out of its first layer is almost identical in both cases, similar enough that a human cannot find the difference, the second layer seems to magically find the difference. All the project files, including the code, dataset, and result images, are on my GitHub. The link can be found in the description. Thank you for watching.